This example is one of the simplest problems for the applications on Newton's law. Here, the object of 4 kilogram mass is held by a rope against the force of gravity, against the weight, and it is in static equilibrium. This is just to show how can we get out of the problem here. We get the free body diagram and then set up the equations as we said before in our strategy for solving such problems. This is a one-dimensional problem. It can be solved easily. Now we can use the free body diagram to find the solution. Now, by using the free body diagram, as long as the body is in a static equilibrium, then the resultant force acting along the y-axis is equal to 0, and we have tension upward and the weight mg downward. Then we have, in this case, T equal 39.2, that is the product of the mass, the given mass, and the acceleration due to gravity. And the problem here is solved. As we applied the Newton's first law in the previous example, here we're going to carry out another problem in 2 dimensions for the application of Newton's first law. Here in this, the system is in equilibrium as the block of mass 4 kilogram is held by these ropes as shown, and it's held in 2 ropes as well. The ceiling, one of the ropes makes an angle of 60 degrees with the ceiling, that is called, it has a tension T1, and another rope making 30 degrees with the ceiling, it has a tension of T2. And also the note here of the ropes is made where there is another rope here holding the block, and this has a tension T3. And now we assign the forces as in our strategy acting on each point. There are 2 points here, one at the object where there are 2 forces acting on it, 2 forces, the T3 upward and mg downward, and here at the junction here at this node we had 3 forces. So we need to draw 2 body diagrams, one for the mass and the other for the joint of the ropes. At point, call it O2, the origin 2. Here we are, this is the free body diagram for this origin, at this origin. And also at the point, the other origin O1, where the block is there, we have also another free body diagram. So we're going to use these diagrams in order to set up our equations and solve the problem. What is wanted here is to find the tension in the 3 loops T1, T2, T3. To do that, we have to get 3 equations out of these free body diagrams in order to solve the problem. Now, at point O1, we have as the system is in static equilibrium, we have a resultant force here along the y-axis equals 0, and the forces that contribute in this sum is T3 upward and mg downward. In this case, we have T3 equal 39.2 because the mass of the object is given as 4 kilograms. And multiply that by g, acceleration due to gravity, you'll get this answer. Now at the other point in the second free body diagram up, we have resultant force along the x-axis equals 0, and also the resultant force along the y-axis must be 0 because the whole system is at equilibrium. For the x-axis, we need to break the vector T1 into its component and the vector T2 as well, while the vector T3 is already along the y-axis. For T1, we'll get T1x, this one, which is T1 cosine 60, and for T1y, we got this one, that is T1 sine 60. Likewise, for T2, we have here T2x, which is minus T2 cosine 30 because the component is heading due west. And again, also we have along the y-axis a component for T2, that is T2 sine 30. So this is the components along the x-axis. You just put the values of the angles, and then we get this relation T1 equal 1.73 T2. So to get the other relation, we set up the equations along the y-axis due to Newton's first law, and then the forces along the y-axis in the upper diagram is T1y plus T2y minus T3. By using also the angles, the given angles in the equation, we're going to get this equation 0.86 T1 plus 0.5 T2 equal 39.2, and here we substituted this value for T3 into this equation in order to get this one. Now we have from this equation together with equation this one and this one, when you solve them simultaneously, you will get T1 equal 34.1 Newton and T2 19.7 newtons. This is a simple problem as an application to Newton's second law, and in this problem we have this black block is sliding along the surface of smooth incline, and this incline has an angle of 30 degrees with the horizontal as shown. So the question is, what is the acceleration down the 30 degrees incline? To solve this problem, we have to follow our strategy. First of all, we have to assign the forces acting on the block, and this is the weight downward as always the case. And here the inclined surface has a normal force pushing the block upward in this direction. The second step is to draw the free body diagram, just drawing the forces as vectors in the XY plane. And it's important here to note that when you have an incline, you have to always just take the x-axis along the incline and plot it as is, this way. And then we have along the y-axis, which is perpendicular here to the x-axis, Fn, normal force, and we have the weight downward. The angle 30, we can get it here easily from the diagram. If you plot this perpendicular here to the surface, this is the perpendicular to the surface. The angle here 30 This means if I get the weight like this is the weight downward. Obviously, if this is 30, this is going to be 60. And by having this 60, 90 degrees, this one is perpendicular to this one. Obviously, this angle is going to be 30, here 30. That's why we have it here 30, the same as the angle of the incline. So usually the angle between, when we have a body on incline, the angle between the weight and the normal to the surface is the same as the angle of the incline, as we just demonstrated. Now the second step is we have to set the equation along the x-axis. What we have along the axis, we have an acceleration, and multiply that by the mass. This is the net force along the x-axis. Now, what are the forces acting along the x-axis? As you can see here in the diagram, the weight here, mg, is decomposed into two components. One along the y-axis, that is mg cosine theta, and one along the x-axis, that's mg sine theta. So from the diagram, as there is no friction, the only force acting here in this problem on the body along the incline or along the x-axis is mg sine theta. So in this case, mg sine theta equal m times ax, and we can get the acceleration as g sine theta by inserting the value of theta of 30 degrees and acceleration due to gravity. You're going to get the acceleration of the block as 4.9 meter per second square. Along the y-axis, actually we don't need the information along the y-axis as long as the friction is absent, but it's necessary here just to write down the resultant force along the y-axis, because the system along the y-axis is at equilibrium, which means that the block doesn't go up or down while during its motion. So that's why the net force along the y-axis equals 0 due to the first Newton's first law. What we have along the y-axis, we have a normal force upward, and we have mg cosine theta downward. Then we get the normal force equal mg sine theta, and we don't want that at this moment. But when we have a friction, we might need this equation. Now, unlike the previous case, we're going to use a rough incline instead of smooth one. And we're going to find again the acceleration of the object while it's moving down the 30 degrees incline. Well, to do that, we need to assign the forces acting on the object, on the block as it's moving down. That is the weight, which is directed downward, and the normal force, which is the force acting from the incline perpendicular to its surface on the block, and then also the force of kinetic friction. Then we replaced here the force of kinetic friction by that of previous cases of static friction, because in this case we'll have an acceleration and a motion down the incline. Now we draw the free body diagram as before, where the weight is decomposed into two components, mg sine 30 and mg cosine 30, and the force of friction is opposite to the motion of the object and this force of friction is nothing more than the product of the coefficient of kinetic friction, which is given in the problem, and the normal force. Now the first step is to set up the equation along the axis. That is the net force, which is the product of the mass and the acceleration along the x-axis. On the right hand side. On the left hand side, we need to know what are the forces contributing along the x-axis. It's obvious here that we have the component of the weight mg sine 30 is acting towards the positive x-axis, while the force of kinetic friction is opposing to that, which has a negative sign. Then by inserting mu k Fn for Fk, for the force of kinetic friction, into this equation, we got the information about mu k and theta. What is left is we need to know what is Fn. To get Fn, we need to know what are the forces along the x-axis. The net force along the y-axis. The net force along the y-axis is 0 because along the y-axis there is no motion, neither upward nor downward for the block. So what are the forces contributing along the y-axis? We have the normal force upward with a positive sign and mg cosine theta with a negative sign. This gives us Fn, which is mg cosine 30. We substitute this into the previous x equation, and then we'll get this equation. Then to solve for the acceleration, we just insert all the values given in the problem, and then we'll get an answer of 1.5 meter per second square for the acceleration along the x-axis. This example is an application to Newton's first law. Well, in this example, we're going to find the critical angle of a smooth, a rough incline called theta sub c. This critical angle allows the block to be just about to move or on the verge of skidding. And this angle will be expressed in terms of the coefficient of static friction. To solve this problem, we're going to set the equation along the x-axis from the free body diagram, as the weight is decomposed into two components, mt sine theta along the x-axis, and the maximum static force of friction opposite to that, and this is the static force that opposing the motion. And also we have another component for the weight along the y-axis, mg cosine theta, opposing the normal force. To solve that, we have to substitute mg sine theta sub c, and we have to substitute the force of static friction, which is the product of the coefficient of static friction mus and the normal force Fn. Obviously, this is the only case for static friction that we can write the product in this way. That is for the maximum static force of friction only. Now, to solve the problem, we need another equation that is along the y-axis, and the resultant along the y-axis equals 0 as long as the block is in static equilibrium. So what we have, what forces we have along the y-axis, we have, as we said before, the normal force in the positive direction and mg cosine theta in the negative direction. So this gives us equation 2, Fn equal mg cosine theta. By solving these two equations, 1 and 2, and we can get an equation for tan theta equals the coefficient of static friction mu sub s. Then obviously the critical angle is equal to tan inverse mu sub s. This part is also another application to Newton's first law, but this time we're going to allow the block to slide down the inclined surface with a constant speed under the effect of the force of kinetic friction as well. So in another meaning, so we're going to have the net force along the x-axis 0 as before, but this replacing the Fs maximum in the previous case with Fk. And as you know, the force of kinetic friction, Fk, is the product of coefficient of kinetic friction and the normal force. So again, what is required here to find is the critical angle theta sub ck, and this angle is the angle that allows the block to move down the incline with a constant speed or constant velocity. And to solve the problem, we're going to follow the same strategy as before in part A, the first part of the exercise. And here we make our sketch and draw the free body diagram. The resultant force along the x-axis is going to be 0 because the block is in equilibrium because it's moving with a constant velocity. And the forces acting along the x-axis is mg sine theta minus the force of kinetic friction, and the force of kinetic friction, as we said before, is the product of mu k times Fn, the normal force. So we put that in here, and then we take the second equation along the y-axis as the resultant force equal to 0 because of course there is no motion along the y-axis. And here we have Fn equal mg cosine theta. We solve the two equations in order to get theta c sub k, and theta c sub k is nothing more than tan inverse mu sub k. We have to measure here very important notice as we compare this part to the previous one. The previous one we got theta, the critical angle, as tan inverse mu sub s, that is tan inverse the static force of the coefficient of static friction. And in this case we got the angle tan inverse mu sub k, and mu sub k is the coefficient of kinetic friction. As we know, the coefficient of kinetic friction is always less than the coefficient of static friction. So that's what lead us to conclude that the angle of kinetic friction, the angle of the incline, the critical angle in this case, is less than the critical angle in the previous case. In another sense, that the force required to let the motion moving with a constant speed, Fk, competes with mg sine theta. So to keep it moving with a constant speed, Fk here is less than the corresponding force, that's Fs maximum in the previous case, that keeps the balance with the mg sine theta. That's why here the critical angle is less than that of the previous part of the exercise.